Very soon, I will be retiring peacefully to start working as a social entrepreneur. Social entrepreneurship is an approach by individuals, groups, startup companies, or entrepreneurs in which they develop, fund, and implement solutions to social, cultural, or environmental issues.
Your teacher Michael Aendera from Nairobi, Kenya.
Jina langu ni Beatrice Dube, mwalimu mwenza wa Bwana Michael Aendera, na nina furaha sana kujitolea kama mmoja wa walimu katika mradi huu wa Kiswahili tekelezi.
Good evening, good morning, good afternoon, wherever you are. My name is Eric Udur. I currently teach at State House Girls High School. Personally, I teach physics and mathematics, and today I'll be taking us through a physics lesson from 2. So I'll have to log in my second device very fast. Won't take long, and then we will just continue with the lesson. So just in seconds, my second device will be on. Meanwhile, as I log in my second device, I can see it is ready for admission. In case my audio is not very clear, as I've always said, you can signal me so that we work on it. Okay, fine. So we are set. So I can see many participants. I can see Nduru Mixed. I am able to see Nduru Mixed. Good evening. How are you? For today. Okay, good. So I can see Kagonya Secondary. Good evening. How are you people? Kimuchu, I can see you people. Wow, that is very great. That is great. I can see you people. Nile Road, you are just my neighbors. Yeah? How are you people? Okay. That is great. So I will take us, I have to start my presentation. Today I'll be taking us through a physics lesson. So as usual, I'll begin by sharing my screen. So as I've always said, make sure you are able to see my screen. So as I said, I'm going to take us through a physics lesson. You are able to see what is displayed on the screen. So the main objective of this lesson is that you should be able to do calculations involving waves. And I know we have waves 1 and waves 2. I know for those of us who have interacted with the entire syllabus for physics high school, you know that we have waves 1 and waves 2. So waves 1, we'll be covering that later, maybe our other lessons to come. But for this particular lesson, we are going to be focusing on waves 1. So we are going to do majorly calculations involving waves. And I'm trusting that by the time we are done with this lesson, as students of Nduru Mixed, trying to see the names of schools that are there. I'm trying to see Kagonya, Kenyatta Girls, wow, Kimuchu, and many other schools that I can see, Nile Road and the rest. You will be able to at least be in a position to do what? To calculate or do calculations involving waves. So that is basically what we are going to be covering for this lesson. So let me see. Okay, just a minute. So as we have seen in our previous lessons, for those of us that have gone through this topic before, we know that waves are basically disturbances. Like right now, you are able to hear me speak just because of disturbance. Remember, in the vocal cords, their vocal cords begins to vibrate as I talk, and then that vibration interacts with the air particles, which also begin to vibrate. that is picked by the signals. I mean, the devices I'm using here, which are able to convert them into radio waves. They are transmitted to where you are. Finally, they are reconverted back to disturbances using the devices that you are using currently. And then that disturbance is transmitted to air. Then as air vibrates, it finally reaches your eardrum, which also begin to vibrate with the same frequency, and that's why you're able to hear what I am saying. So the topic that we are covering today is quite relevant because you are able to hear what I'm saying this evening because of waves. Of course, this one you have covered in our previous discussions. So I'm just mentioning this because this is part of what we have covered in our previous lessons. So this is energy. We normally say that there is a principle called the principle of conservation of energy, which says that you are not able to destroy energy, neither are you able to create energy. You can only be able to transform it from one form to another. And therefore, when you talk about sound and you talk about waves in general, these are just other forms of energy which are transferable from maybe the source to other destinations. So these are examples of waves, like water waves. When you get close to where there is a large mass of water, you could see tides on the surface of water. And those are the waves you are calling water waves. Now, for those of us who have listened to music, we have waves that are generated as somebody plays a musical instrument, just like a guitar. When one string is plucked and sound is produced, a sweet melodious sound is produced. That is an example of waves on a plucked string. And of course, we have sound. I just demonstrated sound. And then, of course, there is this other wave. We can call it wave. You can call it energy. Energy waves. Because waves transfer energy. That's why we are able to get energy from a wave. So somebody could call them energy, forms of energy, or we could call them waves. So we have this one we call light, the one that enables us and other animals to see. We call it light. So these are just examples of waves. So there is this way of categorizing waves. We have done this before. Waves can be categorized in terms of electromagnetic or mechanical. Now, that is just one of the ways of categorizing waves, as we have seen before. So the ones we are calling electromagnetic are those ones that will not require a material medium for them to be transmitted. An example is light. You see, light can move even without a medium in between. But then we have those ones that will require a material medium for them to be propagated, like sound. Without a medium, like right now, you are able to hear me because of the medium called air. Sound travels through air, sound can travel through water, and sound can also travel through a solid medium or a medium in a solid state. So there are those that will require a medium. What that means is that if there is no medium, you are not able to do what? They are not able to be transmitted from one point to another. An example is sound. If you don't have a medium of transmission like air, let's say in the rooms where you are, like at Ndoro Mixed and these other schools that I can see here, we have Ndoro Mixed, many other schools here, St. Mary's, Ukwala, Kimuchu, and many others. If we didn't have air in those rooms where I can see the students are seated, possibly sound will not be transmittable from the devices. Remember, we are having this sound produced from where I am, getting into the devices which convert them to radio waves. Radio waves, you can see radio waves, that is an example of electromagnetic waves. Then the devices, once they are converted, they are transmitted to where you are. The devices you have there will pick them and convert them back to vibrations. And then those vibrations are only transmittable to your ears, to the eardrums, if you have a medium air. So if someone would suck out all the air, you'll not be able to hear what I'm saying this evening. So we thank God because of the medium air that is able to help us communicate effectively without distances becoming a barrier. So electromagnetic, what I'm saying is they don't need a medium for them to be transmitted. These are waves that do not need any medium, any material medium for them to be transmitted. Other books or other literature materials could talk of, they can be transmitted through vacuum, vacuum. Then mechanical waves, they are only transmittable through material medium like air, water, and so on and so forth. So I've given you examples here. Of course, this is something we have done before. So should you have any questions on this, you are free to type in the chat box. You are free to put up your hands, and then we'll be able to clarify. Now, other than categorizing waves in terms of electromagnetic or mechanical, waves can also be categorized in terms of transverse and longitudinal. Transverse or longitudinal. So in the previous case, we said you could categorize waves in terms of electromagnetic or mechanical, depending on whether they need a material medium for them to be transmitted from one point to another. Now, in this case, we will look at the nature of vibration. We will look at the nature of vibration. Let me see if I'll be able to write something on the screen. So maybe we could have the particles vibrating like this, but then you can see how that wave is moving from point A all the way to point B. So the direction of the wave travel is like that, but the particle, remember we normally say that these vibration particles, like right now, I've got a lot of vibrations happening in the vocal cords, you know, my throat, in the voice box of human beings, like now I'm talking. We have got the vocal cords doing a lot of vibrations, but my vocal cords are not reaching where you are. It's the energy that is transferable. So the vibration can happen without the particles moving, but that wave can travel. So like right now, the wave is traveling to where you are. Like point A is State House Girls, point B is Nur Kimuchu, Kimuchu Secondary School, or which school? St. Mary's Ukwala and many others, Kagonya and many other schools that are there. So point A, this one is State House Girls, and this one is now where you are. So the wave is actually traveling, but the vocal cords are vibrating. You see, that is if it was that kind of a wave that vibrates like that, up and down like that, and then the direction is like that. You see, when the vibration is perpendicular to the direction of the wave travel, we call that longitudinal. So we've talked about, this is the path, and then the wave is traveling towards that path, towards that direction like that. So this is point A, and this is point B, you see. So the wave is traveling from point A to point B. That is the energy. Like now I'm talking here and you're able to hear me in Nduru Mixed, but then the vocal cords are vibrating like that. Somebody should not write on my screen. I'm the only one who is allowed to write. So if you have that kind of vibration happening like that, then this is the first type here, the transverse, transverse wave, you see. Then we can also be having the particles vibrating like this, horizontally like that. Then at the same time, the wave is traveling in that particular direction, you see. See. Then in that case, we'll be calling that wave longitudinal wave. So it's this case here, longitudinal. So we say, how are the particles vibrating relative to the direction of the wave travel? You know, if you look at the way the wave is traveling and the way the particles are vibrating, either they vibrate and travel along the same direction, we call that parallel, then you end up with a longitudinal, or up and down, and like that, they're perpendicular to each other, you call that transverse. So that is part of what we have discussed in the past, and I really believe that you should be able to handle that with ease. So transverse wave, the particles displacement is perpendicular. So when you talk about particle displacement in this context, that is the vibration I was talking about. They are being displaced up and down, you know, or horizontally like that. Initially, the particle was here, and because you added more energy into the system, we call that increase of kinetic energy. The kinetic energy, it is the energy that is responsible for motion. Every time you see a particle move or an object move, like you see, there must be energy. There must be energy. You see, so if you give it more energy, it can either move in this direction or it can move in that direction, you see. So if the wave is moving like that and the particle is vibrating up and down, then we are saying they are being displaced perpendicular to the direction of the wave travel. That's why we're talking about a wave in which a particle displacement is perpendicular to the direction of the wave propagation. Propagation is the travel. Propagation, like right now we can talk about sound is propagated from State House Girls to Nduru Mixed. or to St. Mary's Ukwala. That is propagation, movement of that energy. It is being propagated. So we use that term in science to mean that movement, propagation. So this means that as the wave travels, the particles of the medium move up and down. I've already talked about that, and that will give us transverse. There are examples there, water waves and light waves. And if you have questions, please be free to ask. Then, of course, the longitudinal is the one that we have the vibration is happening parallel to. So waves, the particles displacement is parallel to the direction of the wave propagation. We have the examples there, sound waves, and of course, we have those ones that happen when every time we hear of something called earthquake. So this is an example of a transverse wave. Transverse wave, you can see the particle is vibrating up and down, but then the wave is traveling from point A to point B. So the two are perpendicular to each other. You see, like that. So there are these terminologies that are used here. Phase, phase, phase. What is phase? So we normally say that particles are considered to be in phase if they are moving in the same direction, yeah, they are at the same point, moving with the same speed and in the same direction. They may not necessarily be in the same point for that matter, but as long as you have the direction being the same and speed being the same, then such particles can be considered to be in phase. Yes, they can be considered to be in phase. I know we have also covered that in our previous lesson. That was not really the main objective. So we have particle at this point is tending to move upwards. That's why the maximum displacement here is here. This means this particle at point A was beginning to move up. If you look at another particle at this point, is moving up. Another one at this point is tending to move up. That's why the maximum displacement is there. At this point also is beginning to move up. So we have got X, Y, Z, and M. The particles at those points are considered to be in phase. Why? Because they are in what? They are moving in the same direction, and of course, they are moving with the same velocity. So direction and velocity determines whether the particles are in phase or out of phase. So that is, then there is this term we have used here, wavelength. Layman way of looking at wavelength is simply the length for one wave. One wave, yeah, one wave. Let me try to demonstrate. At this point, the particle is moving upwards. Then you go until you get when the particle is beginning to move upward at the same level of displacement on the horizontal line. At that point, we are considering that point one wave. So somebody would simply call it the length for one wave. You see, normally say that don't try to use the same term to explain the term. So if you say wavelength, the length for one wave, it's not a good definition. You cannot use that to define what wavelength is. But then I can use what I have just described, the phase. I can say, remember we had phase at this point, another phase, phase, or we are saying those points are in phase. So somebody could call wavelength the distance between two successive points. That word successive is very important because now you could talk about the distance between 2 points that are in phase. Somebody could pick this point and the other point, but that is not wavelength. So the word successive, successive is very important. So we are talking about points successive in phase. Yeah? 2 points successive, they are in phase. That defines what wavelength is. So we say the distance between two successive points on a wave which are in phase. We call that wavelength. So if somebody was to ask us, find the wavelength for this wave, and it is just length, as I say, it's the length of one wave. That means somebody can easily ask you, state the SI unit of wavelength. So because it is length, we know what the SI unit of length is. Can somebody tell me what the SI unit of length is? Can I get any response from any school, any student from any school? Kagonya? Any student? Can you tell me what the SI unit of length is? The SI unit of length, any school? Can I get
Mwalimu Nduru Nduru Mixed has raised the hands. Nduru Mixed.
Oh, Nduru Mixed. Yes, Nduru Mixed. Nduru Mixed. Can I get a response from Nduru Mixed? You can either say it via audio or use of symbols or texting on the chat box. There's a unit of length. Nduru Mixed.
The SI unit of length.
Come again, I didn't get. I only had the SI unit of length. The other bit I did not hear. I beg your pardon.
The SI unit of length is meter.
Is the meter. Yeah, we normally say that when you are trying to state the SI units, you try to make them singular unless otherwise. Yeah, you say the meter, ta. So you try to avoid using that S at the end. You don't pluralize. So you say SI unit of length is the meter. And we say you try to avoid this M as much as possible. So most of the time when we mark student scripts, they like giving this one here. See? We just ask them, what is the SI unit of length? Or can you state the SI unit? Then you just see a student writing this one here. So we try to discourage that. We try to discourage that at all costs. So just state the meter. The meter. This one is very, very important. That is the SI unit of length. And therefore, because wavelength is also just length. You know, the second part talks about wave, and the second part is talking about length. So wavelength is just the length. Yeah, so we're expecting you, if you are to state the value in SI unit, then it's supposed to be in meters. But of course, I know this one can be given in millimeters, you see? Yeah, millimeters. It can be given in millimeters. We call them multiple or sub-multiple units. Sub-multiple units, like milli standing for 10 power negative 3, you see? Centi, 10 power negative, you see? So when you say centimeter, this C here stands for centi, which is 10 power negative. So if you say 1 centimeter, it means 10 power negative 2. Centi stands for 10 power, or 1 over 100, depending on how you want to look at it. 10 power negative 2 over meter. You see, so it means the wavelength can be given in centimeter. Those are basically prefixes that we use in unit conversions to help us come up with smaller unit quantities like centimeter. If the length is very small, you could decide to measure it in millimeters, centimeters, and so on and so forth. You see, kilometer, it's just meter. It means if somebody said that the wavelength is 10 kilometers, you should not get shocked. Teacher Eric teaching us about this concept never mentioned wavelength to be measured in kilometers. They have just added another prefix there, K, K. It is just the meter, but now if you talk about kilo normally stands for 10 power 3 or 1,000. So if you remove K there, you'll talk of 10 times the K, which is 10 power 3 or 1,000 over meter. So that means 10,000 meters. So if the wavelength is given as 10 kilometers, don't get shocked. Don't get surprised. Eric never talked about that. So we know this is the SI unit, is the standard unit of measuring that. Okay. So wavelength. So we have said the wavelength. So wavelength, if this here must be given in terms of centimeters, kilometers, I was talking about the SI units. Kilometers, cent, I've already talked about. Millimeter. Can somebody give me another prefix that can be used? These prefixes that we use to do unit conversions, apart from kilometer, centimeter, millimeter. Can somebody give me another one? Which school? Oh, I can see Nduru.
I'm seeing the hand Mwalimu from Kimushu. Yes, Kimushu, Nduru, even St. Patrick's have raised their hands.
St. Patrick's, yes. Give me the other prefixes, St. Patrick's. Another prefix that we can use. That is very important. Yes, there is hecto, so somebody can give hectometer. Another one. Yes, from Nduru. I don't know whether that was Nduru. I didn't get that, but Yes, I can see St. Patrick's. Yes, St. Patrick's, I can see your hand is up. Come again. Okay. Okay, so all those that you've said, I know you know them. So as long as, okay, that is enough. That is enough. Now you can just mute so that you continue. So now, as long as you use all those prefixes here and the last word here is the meter, then you know they're now talking about wavelength, or rather, that information is able to help us get the wavelength. Wavelength. That is very, very important. I'm going to tell you how important that is, especially when it comes to calculations involving waves. That is very, very important. So this is going to give us, so if, let's say this was given as 6 centimeters, then basically you are able to use that to help you calculate the wavelength, the length for one wave. So you're going to ask yourself, up to this point, how many waves are there? So I can see one complete wave is there, another complete wave is there, one complete wave is here. So how many complete waves are there? 1, 2, 3 complete waves, giving us 6 centimeters. So this unit here could vary depending on what the examiner is looking for. It could be centimeter, it could be kilometer, it could be millimeter. So every time you see that, you know, this information is relevant in calculating the wavelength, the length for one wave. So you'll say, wavelength, we normally use the symbol lambda. It's one just of the Greek alphabets, the lambda. Yeah? So I'll say 3 lambdas. That's how we write lambda. That is small letter. Just like we have capital N, small letter A. So that is small. So we have 3 lambda is equals to 6. So how do we get 1 lambda? So for us to get 1 before lambda, we need to divide both sides by 3. This is maths. This is mathematics. I'm also a math teacher, so at least I am sure of this. So lambda 3 will cancel 3. 3 goes with 3. Then 6, 3 goes into 6, 2. So you will maintain the same units used here. So if it was millimeters, you'll write millimeters. If it was centimeters, you'll write centimeters. So it means the length for one wave is 2 centimeters. That is wavelength. The length for one wave, yeah, is that one. You see? Wavelength. Okay? That's how you get the wavelength. Sometimes you could also be given this, 2, 4, and then 6. An examiner can be lenient enough to give you this, but if it's given, then just take it directly like that. Just say wavelength is equal to what? 2. Teacher Eric, while teaching about this concept, said that wavelength is just the length for one wave. That is a layman way of looking at it, without going into the scientific, the jargons, the scientific terms. We talked about the distance between 2 successive points in a wave which are in phase. That could be a little bit complicated, but that is the right definition. If somebody was to ask you that in an exam, that is what you're supposed to write. But if you are to make somebody understand what that is in simple terms, in layman terms, you just talk about length. How long is one wave? The wave is starting from here and ending at that. How long is it? How long? Okay, good. So we are making very good progress. Any questions up to where we have reached about wavelength? Wavelength, the unit used for wavelength. Any question? Somebody asking a question? I'm waiting for somebody to ask a question. Anybody?
Let me help you, Mwalimu, to see the schools which have raised their hands, and then I'll tell you.
Okay. So as we wait for any schools that are trying to seek clarification regarding what we are trying to learn, we can continue a little bit. So there is also this term called amplitude. Amplitude normally determines how loud or the energy carried by. Sometimes the water waves can be so much to an extent that the transportation, the water transport is actually affected. The ships are not able to move through water because the waves are so much. What determines how much energy a wave carries is what we're calling the amplitude. Amplitude, you see, amplitude, the maximum displacement. You see, like this one here, you could talk about this one here. how much displacement is this? So you can see this is 4 millimeters. Again, the units here are very important. So that is amplitude. We normally call it the maximum displacement of a particle on either side of the mean position. This particle started from here. That is where it was initially. Then finally it has been displaced. So if you have this and you have another one that is going to that, then you'd say that this one carries more energy. So if it was a water wave, it is quite more risky to travel through that water, because now the energy carried can be catastrophic, can cause some danger. You know, it is quite dangerous to travel through that water because of the energy carried. And what determines the energy, or sometimes you can call it the intensity, is the amplitude. So we simply define amplitude as the maximum displacement on either side of the mean position. Amplitude. So this one you simply read from the graph. Like here, it is just this one here. So somebody can just say amplitude is the symbol, just like wavelength, we say the symbol is lambda, amplitude is capital A, and you'll just extract it from here. So you say 4 millimeters. Again, milli, the first M stands for milli, which is 10 power negative 3. So if somebody was to ask you to state the amplitude in the SI unit, which is the meters, somebody already told us, you can simply say that A in meters should be equal to 4 times 10 power negative 3 over meter. The negative 10 power negative 3 is replacing the first M, which stands for meter. And this will give us 0. This one you can do using the calculator. We know we use the calculators a lot in physics. So this is going to be 0.0004 over meter, you see. So you can either state it as 4 millimeters if the examiner is silent on the unit in which we're supposed to be presenting the answer, or sometimes the examiner can be specific and they could talk of, could you state the answer in the SI unit or could you state the answer in meters? Then you need to just replace the first meter by 10 power negative 3 or 1 over 1,000, depending on which one you find easier to master. And then you're still going to get the same thing. Of course, you need to use a calculator. I've tried to do it often. I didn't use a calculator because I've done it quite a number of times. But there is no harm in also confirming if the answer that you have gotten is right. That is, you simply need to use a computer, you see, to do that. I already talked about phase. Now, there is this one here called frequency. Note, before you ever go to frequency, there's what you call period. Period, we use T. Period now is the time for one wave. I told you now we time for one wave. We look at the layman way of looking at it, then we now go to the real science. So period, how much time does it take for this wave to travel from here to here? It started from that point. Then on reaching this point looks exactly like this point. We say the 2 points are successive and then they are in phase. The particles at those points are moving in the same direction and with the same velocity. So we call that what? Period, time. Just the SI unit of time will be used for period because this is time for one wave. Can somebody tell me what the SI unit of time is? You can type in the chat. Oh, somebody sent a question from Nduru, and the question is quite interesting. Okay, so before I go to that question that is asked by this team from Nduru, let me look at this, the period. So period is the time for one wave. So you look at the one wave is here, how much time did it take? You see, how much time did it take? So time, the SI unit of time is the second, and therefore we expect if somebody was to ask you to calculate the period in SI unit, then you'll state the answer in seconds. So you'll talk of maybe 2 seconds. 3 seconds, you see. So what that means is that, how do you know whether a question is requiring you to calculate the period or the wavelength? Because now that distance, at one point I was saying it is wavelength, but now again, after a few minutes, I'm now saying it is period. So which one is which? It can be confusing. So we should not allow ourselves to be confused. So how do you know? In the other case I said, if you see units used for length, like the SI unit for length is the meter. Then we could add other prefixes like centi, milli, and so on and so forth. So you know that wavelength. Now time, the period, If you see seconds, milliseconds, could you give me the other prefixes that we used? Somebody? Centi, you know, any prefix that is used there, you should not get confused. So if you see that, then you know in this case, this question, the examiner is keen on me calculating what? The period of the wave, the periodic time. We normally call it periodic time. Periodic time. Periodic time. T is the symbol used. So T in physics, we use it for, I know somebody is asking, there is a time you were using this for tension, the force. If you stretch a string, you stretch something, the force experienced by that stretched object is called tension. So we also use T to represent that. But that symbol is also used in physics to mean periodic time. So normally you check the context. Every time you are reading a book and then you come across that letter T, reading physics literature, maybe physics textbook or something of that sort, and you come across letter T, capital T, then it could mean one of those two among others. We are going to look at some as we continue with our syllabus, physics syllabus. But for now, I know you've talked about tension in Form 1 work. Form 1 work, we talked about types of forces, and there was tension force experienced by stretched object. Now we're using the same symbol again to represent periodic time. So it depends on context. So if you're talking about waves and you see T, you are reading the topic waves and you see T, then most likely that represents the periodic time. Yeah. Periodic time. So the same thing we did. We said just count the number of waves. 1, 2, 3. So we say 3T is 6 seconds. So how do you get 1T? You simply divide both sides by 3 again. So you get T is equals to what? 2 seconds. That is the time for one wave. Time for one wave. Now this one normally leads us to something called frequency. So frequency, we use symbol small letter f. That's how we write small letter f. But then this frequency now, we want to see, because now this is disturbance. Disturbance is all about vibrations or particles. The other time we're talking about particles vibrating. So we are finding out how many particles or how many vibrations do we have in 1 unit time. 1 unit time. When I talk about unit time in this context, we are talking about the SI unit, 1 second. How many vibrations are there in 1 second? So somebody could talk about how many oscillations. Oscillation in this case could mean oscillations, to and fro movement. We started from here, we went up and returned back to the same point. We call that an oscillation. The reason I'm reintroducing that word oscillation is because different books are written by different authors, and you're likely to interact with all these books. So other books could be talking about number of vibrations per second. Other books could be talking about number of oscillations per second. And other books could be talking about number of complete waves in 1 single second. If you take 1 single second, how many waves can you see? Yeah. Like in this case, if you want to know what the vibration, you may not be able to see 1 second. It's not anywhere, but you are able to approximate scientifically. So you are not able to see 1 second anywhere, but you are able to approximate. You could say that if these are 3 waves, 3 waves, 3 complete waves in 6 seconds, how many waves are we like? This is more of maths. How many waves are we likely to get? How many waves in 1 second? That's what we're calling the frequency. In 1 second. So you'll do what we do in math, very simple, cross multiplication. When you are dealing with proportions, that's what we do. Proportions. Anyway, I don't want to drag. We simply multiply it like that. So 1 times 3, you divide by 6, and your calculator will give you 0.5. But then remember, we said calculations in physics, unless they are ratios, they're supposed to have units. Ratios normally don't have units. But now, unless they're ratios, they're supposed to have units. So what unit do we use for? So we use hertz. This one is written like that, but the symbol we use is H capital and Z small letter or Z small letter, like that. Yeah. That is the symbol we use for frequency. It simply represents the number of oscillations, the number of waves in 1 second. How many are there? So this one, you only have half a wave in 1 second, and that quantity is called frequency. The SI unit of frequency is hertz. Yeah, hertz. That's how we do it. Now, we normally say that frequency is the inverse of the periodic time. So you can also use the formula, and the formula for frequency is normally this. Just like we have pressure is equals to force, supposed to be capital F, over area, we also have frequency. We also have a formula for frequency. Remember, physics majorly we look at quantities, their symbols, basic descriptions of those quantities. We look at the SI units, we look at the characterization or the types, and then most importantly, the formula. Very, very important. Those are key concepts that are tested in physics. Formulas. So formula for frequency, we normally have the reciprocal of the periodic time t. 1 over t. So instead of doing that comparison, that you're saying that if you have 3 waves giving us 6 seconds, or 3 waves in 6 seconds, how many waves is there in one second? Because the definition of frequency is that the number of complete waves in a second. Instead of doing that comparison, you can simply use the formula and it will give you the answer very fast. Remember, I'm talking about calculations involving waves. So you'll say that 3t is equal, because now the formula here has got t. I'm looking for f, but the formula has got t. So what that means is that I'll have to start by finding t. You'll have to start by finding t. So this t is important. 1 is constant, so t is important. So it means I'll have to go back. It's like you're building a house and then you realize that this house, maybe it is complete, but the doors are not there. You really need to have to get the doors first before you do your completions, the final touches. So I'll have to find this t first, t. So I'll go back to the formula. 3t is equals to 6. It means then you divide both sides by 3 so that you get t is equals to 2 seconds. So you come back to f and you say f is equals to 1 over t. So this is going to be 1 over 2, which will still give us 0.5 hertz. Somebody would say that, why can't you give just the answers half? We normally say that in physics, if you are not supposed to give the answers, final answers, in fractions. That's why you know the answer there, 1/2. I still have to simplify it to 0.5. So that's supposed to be the final answer for that. So that is frequency, how we calculate frequency. I've talked about how we calculate the periodic time. I've talked about how we find the amplitude. I've talked about wavelength and how we find the wavelength. And I don't know whether we have questions on the same, so that at least I can be sure we are following. There is this group from Nduru asking me, kindly explain how to determine the wavelength of a longitudinal wave using rarefactions and compressions. Possibly that is what is going to form part of our discussions for our next lesson. So allow me not to talk about it today. I know it is very possible to talk about, to find all these things that I've talked about. Remember, this is transverse. So the next week or the next time you're having a lesson on the same, I'm going to be focusing now on a longitudinal, so that you see how we can use rarefactions. You know, now you ask that question, somebody's wondering, what are rarefactions by the, what are compressions? So we're going to talk about that the next time you're having a class. Yes, exactly. So if there are no questions, I want to allow you to attempt. You see, those things that I've just talked about, now they are here again in question 2. You can see them. You can see the amplitude, you can see the wavelength. Huh? I don't know whether you're able to see the wavelength. But anyway, somebody's asking me then, how do you calculate wavelength from this? Maybe I did not mention that. But wavelength, if you want to calculate the wavelength with this information, because now in the previous discussion, I was saying that you are able to calculate wavelength if this one here is given in terms of maybe centimeters, millimeters, maybe kilometers. Anyway, you can talk about all those prefixes that are used in unit conversion. But somebody's asking me now, how do you calculate? Maybe that is a question I was expecting from us. Maybe somebody to ask me, how then do you calculate the wavelength if you're not given that centimeter, millimeter, and so on and so forth? You are only given time there, which means you can calculate t from that. How then do you calculate wavelength? So wavelength, from that, we normally use something called wave equation. As we know we are getting closer to finishing. We have about 13 minutes to end the lesson. There is something called wave equation. So every time you are attending a symposium somewhere and somebody is asking you how to calculate the wavelength from such a graph, when this one is not centimeter, millimeters, then you tell them we can use wave equation. So this wave equation, this is what it states, that V. Again, it's also possible to prove some of these formulae that I'm talking about. So today I'm not focusing on the proofs, but I'm talking about, I'm focusing more on the formula and how to use them. So V equals to F lambda. This is what we call wave equation. It is possible to prove that for every wave, if you know the speed and you know the frequency and you know the wavelength, then if you take the speed, like this, in this case, the speed, speed is basically distance covered per unit time. Like in 1 second, what length is covered in 1 second, or in 1 hour, what length is covered in kilometers or stuff like that. That's what we're calling the speed. So because this wave is traveling from point A to point B, so in 1 unit time, what distance is it covering? That's what we're calling the speed. So if you know the speed, you know the frequency, you know the wavelength, it is possible to prove that that speed is supposed to be equal to frequency times lambda, or times wavelength. Or rather, if you take wavelength, you multiply by the frequency, the value you get, if it is 10, velocity, you realize that velocity is also 10. Like for this wave here, it is 320. If you take its frequency, you multiply by its lambda here, then you are going to get a value that is very close to 320, even if it's not that. Maybe 320.00009 or something like that, if you have to do that thing experimentally. So theoretically, the values that are given, if you multiply the two, you're supposed to be getting the exact value that we have there. So this is what we are calling wave equation. Wave equation. V is equals to F lambda. V is equals to F lambda. Wave equation. So wave equation, remember now we have the speed, we are given time, so we are able to get T, and then from T we are able to get F, because we said F is equals to 1 over T, and with F and the speed given, we are able to get what? Lambda. So I normally tell students that you can make very good use of this triangle here. We call it formula triangle. Formula triangle. So we say V up here, V is equals to F lambda. So lambda is the wavelength. So if you're looking for the wavelength of a particular wave, you only need to ask yourself, are we given the velocity of that wave? Are we given the frequency? Sometimes the frequency is given or implied. You know, if somebody is giving you the periodic time, definitely they are telling you, you are able to use the periodic time to calculate the frequency. So with that, lambda, will be able to obtain lambda very easily. Yes. So that is how we go about it. So starting with the amplitude, we said amplitude is the maximum displacement on either side of the mean position. So displacement, maximum displacement, is either down here or up there. But of course, if you find negative, you can decide to ignore, or you can just decide to use -4. Remember, displacement is a vector quantity, so direction is also important. But taking +4, I think that is advised more in this context, that is. So we say amplitude A is equals to forward, the units, millimeters, 4 millimeters. That is the amplitude, 4 millimeters, amplitude. Then now frequency. So for us to get the frequency, can somebody remind me the formula that we used? Maybe, so that at least I can be sure that you are following the formula that we used for frequency. So that is amplitude, and then I have the frequency. Can somebody remind me? I can see somebody here. Anybody from Nile Road?
There are ants from Kimushu.
Kimushu, please, go ahead. If you can remember the formula we used for frequency, just go ahead. You can send in the chat, or you can do what?
Please unmute, then you speak.
Okay, so wait for Kimushu to unmute. Can we get any other? Kimushu, can we get Ndoro?
1 over T.
1 over T. And please, in physics, we normally advise students that it is very important you specify whether it is uppercase or lowercase, whether it is capital. So in physics, we normally say that just saying T, saying P, saying A, it's not enough. Remember, somebody can ask you, what is the symbol used for amplitude? And then you just say A. That is not just enough. I know you have done well, you've tried, but I know as we continue with the learning, you'll be able to learn some of these things as we continue. Every time you are stating the symbols, so you are stating the formula, especially if you are stating using audio or verbally saying it, it's always good you specify whether it is capital T or small letter t, because if you say F is equals to 1 over T, a physicist may not be able to interpret that correctly. But if you say F is equals to 1 over T, then a physicist will be able to identify with that so fast, very, very, very fast. I hope you have learned. Who said that? Have you learned something? That was who? I can't remember the person who said that. Okay, fine. So, but I hope you have learned something about that. So you have to, when you are saying, you have to say 1 over capital T, or you can say uppercase T. So you say 1 over capital T. So it means then we need this T, but I said now that T is the periodic time for one wave, so we are able to get it. So what you do here, you simply need to count, because now we are not given this. We already know this is the complete wave, but we are not given that time. So you have to count the number of waves. So I have 1, 2, 3 complete waves. So you say 3 T's should be equal to 1.2. How do you get T? So you divide both sides by 3, and you get T equals to what? 0.4 seconds, because the time there is given in seconds. Also here it is given in seconds, so it is 0.4 seconds. So if it was given in minutes, as you substitute it in the formula, you still have to convert back to seconds. Remember, in calculations here, we are using the SI units. And I will advise students that every time you're doing calculations in physics, please remember to use the SI units. It is very, very important. I know there are few instances when that conversion is never must. But sometimes, because you are beginning, you are just starting to learn physics in Form 1, Form 2, you may not be able to tell the differences. So we normally advise just do the conversions very fast. It's so easy to do the conversions. So we do 1 over 0.4. And from your calculator, which school will help me get this? F is equals to what? Which school? So F is equals to, F for this wave is equals to what?
I'm seeing answers from Kimushu. I'm seeing also answers from Doro. So Mwalimu, you are at liberty. I'm also seeing answers from Awinga girls. So you are at liberty to choose any.
Awinga girls, yes. It's good to hear from you. And also Kagonya. But let me get from Awinga girls.
2.5 hertz.
Yes, 2.5 hertz. That is very, very important, Awinga girls. You know now, you have also learned the art. Now, every time you are stating the answer in physics, you must remember to state the unit. In fact, if somebody just said, if you just said 2.5, I would have really questioned you a lot. I would have said, then you have not mastered something in physics. Very, very important. Every time you are stating an answer in physics, just like I've said, if you're stating a symbol, you must state whether it is you must specify whether it is capital or small letter. Also, when you are stating the unit, you must, the quantity or the value, say 2.5 hertz. Exactly, that is very good, keep it up. And therefore, after getting the 2.5 now, let me change the color a bit and do it somewhere here so that we don't interfere with what you have written there. So here we are doing question Roman 3. Roman 3 is the one we are doing here. So now we want the wavelength. So this is the one I was talking about now here. We have gotten the frequency. We have gotten the, what else have we gotten? Okay, I've gotten the frequency, I've gotten the amplitude, but then somebody's asking, how do you get the wavelength? Can somebody remember the formula, what I said? As we get closer to finishing, the formula that we're supposed to use, if this is given as time, meaning we can only use it to get the frequency periodic time, but then somebody has already told us to get the wavelength. Can somebody remember the formula we used?
Mwalimu, answers are being raised from Kimushu. Let me look for any other school.
Kimushu? Okay. Kagonya? Kagonya, I hope I'm pronouncing it correctly. Kagonya, second.
Kimushu, at Kimushu, the student has come near the mic, please. Give him
Okay,
chance.
Kimushu, please go ahead, Kimushu. Kimushu, come again, please. Oh, we use what is called the wave equation. V is equals to F lambda. So Kimushu is telling us that if you use the formula triangle, V is equals to F lambda here, then if you're looking for lambda, is velocity over frequency. That's very good of you. Keep it. So lambda is equals to velocity over frequency. That's what they say, which is quite accurate. Keep it up. So V over small letter F. So velocity is given as 320, and this other one, F, we have just calculated as 2.5. And what do you get? What do you get as the correct answer? I don't know whether this is clear enough. Let me see if I'll be able to, that is 320 divided by 2.5. What do you get as the correct answer? Can some school, Kimushu, okay, I can see Kagonya, please. Go ahead, Kagonya, please.
My name is Anna Kini. The answer is 128.
Anne, continue. Come again, Anne, from Kagonya.
128.
128, yes, Anne. Anne, you remember now what I said? I said that physics, once you do your calculation, you must never forget to state the unit. Can somebody help Anne to give us the unit for that quantity that we have calculated? The unit, somebody from some school, which school?
Nduru Mixed, Kimushu, they are having their hands up, even a winger. So Mwalimu, you are at liberty to choose any school.
Nduru Mixed, please. Nduru Mixed. The meter. Very good. Now, if I had time, I would have explained why they have chosen on the meter. It is because we are dealing with the SI units. We are calculating using the SI unit. You can see the speed there. The SI unit is meters per second. And then you can see the frequency there. We have used the SI unit, which is the hertz. And therefore, even the value, the quantity you have calculated, it's the value you have gotten there must be the SI unit of length. That's why I was talking about the SI unit of this meter. So now in this case, you are allowed to pluralize. So you can say 128 meters. So that marks the end. Now, I have an assignment here for us. I wanted us to attempt this in groups, but unfortunately, time is not allowing us. I wanted us to attempt this in groups, and then you take pictures and you send to my WhatsApp. That is what I wanted you to do. But unfortunately, time, I don't know, Bwana Bushuru, whether you can give me 2 minutes to do that, or we allow them to go do, and then they will send later on.
No, Mwalimu, let me give you 2 minutes to do that.
Yes, please. So I want us to form groups, in groups of 3. I want you to do this, and then the assistant teacher will be able to take a picture and send it to my WhatsApp number, 0724. You can write it down somewhere. 0724. We'll be able to mark and send feedback in the due course as will be advised by our technician in charge, Bwana ICT expert in charge, Bwana Levi Bushuru. So just note down the number. You form groups of 3, you do the assignment, and then you take a picture and send them to that WhatsApp number before we come to the end of the lesson. So 0724 766, maybe let me write it down on the screen so that you see it, so that you are sure. 0724 766 301. This last digit here is 1, 301. So you take a picture of the students doing it together in groups. You can also take a video if you don't mind doing it in group, and then you also share with me the assignment that they're doing, just in a minute or so. It won't take long. Period, frequency, wavelength. Just 3. Period, frequency, wavelength. It won't take long. Just in a minute or so, you should be done. So they assist, and then as you share the picture of their work and the video of them, students working together, please remember to indicate the name of the school, so that at least as we do the marking and share the feedback on how they have done them, whether they have observed the symbols that we have talked about, They have written the formula and basically what they need to be improving on going forward. At least we'll be sure based on the feedback that you shall have given us, but we need to be sure of the schools that have sent that data. So please, that is what we are doing. This activity session. So I can see Kagonya, they are working in groups. I can see Kimushu, students are working. I can see students, they are trying to copy the question, which is very good. I can see Ndoro Mixed, you are doing well, keep it up. The other schools, your videos are off, so I'm not able to see what you are doing, but I'm hoping that you are doing well. You are doing a great job.
Awinga guys, please put on your video so that Mwalimu can see. Also Nduru Mixed.
Yeah, I can see Ndoro Mixed, they're trying to work out the problem. Can see Kagonya Secondary, you are really trying to work out. That is good, students, keep it up. I wish I knew you by names. Maybe next time I need to be, the assistant teachers, you can be sharing the names before so that at least I get to know the names of these students. This is very good, keep it up, students. We are happy for you and keep up the good work. Yeah, I'll be able to mark, once the data is shared, we'll be able to mark and share with you feedback on basically what you need to be improving on, areas that you need to work on in terms of symbols, how you need to organize the work and stuff like that. And of course, the accuracy of the work as well. Mushu, that is good. Awinga, your camera seems not to be very clear. I don't know whether I'm the one who is not able to see it from this end.
Yeah, Awinga, the camera is not clear. If the room is not lit enough, you can put on your bulb.
I can see Kenyatta Girls. The other schools, I hope you are doing well. I cannot be able to see because your videos are off, but I hope you're doing a great job. Like I can see this, I can be able to see Kimushu Secondary students are really trying to work out. Can advise that you try to improve on speed so that we can wrap it up. You know, we have exceeded by about 5 minutes, but in a short while we'll be concluding. I'm trying to check if there is any that has been sent. That is what I'm trying to do here. Okay. If you're done, just say done. Our girls have to leave. Okay, that is Kenyatta Girls. I hope you have done a good job. You can just share what they've done, the assignment.
Emotion, we are done.
Yeah, you can share the work on WhatsApp. So by and large, I think Bwana Ushuru, I am done. And I want to appreciate you students all for attending the lesson. I hope you enjoyed the lesson. Can I get feedback from any student? Maybe one thing that you learned that as at the time you were starting the lesson, you did not know and you knew as we continued with the lesson. You didn't know when you were starting. Now that we are done, at least now you know it. You basically learned it today. Can I get one student from any school?
Yes, I'm seeing Nduru Mix, Kimushu, Kagonya. Take this opportunity the teacher has given you and take the mic so that you can give a comment very fast so that you cannot get late.
So, Teacher Eric Odur.
Yes.
Start by introducing yourself. A student from Kimushu, please start by introducing yourself so that Teacher Eric can know your name, please.
Okay, sorry for that. I am Haven Mosasia from Kimushu Secondary School.
Okay, Abel.
And I would like to say thank you for the lesson. I know that it has helped most of us, and we appreciate it. Thank you.
That is great, Kimushu. Can we get one more? Then
I don't know, Teacher Eric, if you can give. I'm seeing a student from Kagonya also. They want to speak. I don't know if you can give them a chance.
Please. Yes, go ahead.
Okay, please. Kagonya, go ahead.
My name is Lavenda Achieng from Kagonya Secondary School. I'm happy that I've learned to differentiate between longitudinal waves and transverse waves, and also how to calculate the wavelength. Thank you.
Wow, you're welcome. That is great, Lavender. That is awesome. Keep it up. Sure, I think that is
Any
all. Do you
other
have any
school?
other one?
Any other school before Mwalimu closes this chapter?
Okay.
Okay.
Fine.
I think Mwalimu, there's no any other school. Thank you.
Yeah, that's great. We appreciate you too. That is good. Keep it up. See you next week.
Thank you very much, Mwalimu Eric. I want to take this opportunity to appreciate you and the other global teacher, Madam Betty Kobe, for the wonderful presentation. I also want to take this opportunity to appreciate the presence of St. Patrick's Mixed, Nduru Mixed, St. Mary's Okwala, Nile Road, Kagonya, Jamhuri Secondary, Oyundo, Kimushu, Kenyatta Girls, and I have teachers representing Ngomeni and other schools. So thank you very, very much for your attendance. Until we see you again next week. Asanteni sana na muwe na jioni njema. Asanteni walimu, the assistant teachers, for organizing the same. Thank you very much, Eric and Madam Betty. Thank you very much. We appreciate.
The Kiswate Digital Academy, founded by Pius Odhiambo, is a groundbreaking digital platform aimed at fostering the African Renaissance in the education sector. Specifically tailored for Kenya, the Academy addresses critical challenges in the implementation of the competency-based curriculum CBC for grades 7 through 12 in both junior and secondary schools. Key issues it seeks to resolve include: 1. Access to educational materials. Many students lack textbooks in certain thematic areas, and where available, these resources are often prohibitively expensive. School calendar disruptions. Unforeseen events such as illnesses, pandemics, for example the COVID-19, school strikes, and natural disasters like floods frequently disrupt the academic calendar. 3. Data-driven decision-making. There is a notable absence of reliable online attendance and learning data, which is crucial for informed decision-making in curriculum implementation. Pius Odhiambo, the visionary behind Kiswate, is a trained science teacher and an award-winning data scientist, a philanthropist based in the Washington, D.C., United States of America. His contributions have earned him a place on the Marquis Who Is Who in America, highlighting his international recognition and impact.
Very soon, I will be retiring peacefully to start working as a social entrepreneur. Social entrepreneurship is an approach by individuals, groups, startup companies, or entrepreneurs in which they develop, fund, and implement solutions to social, cultural, or environmental issues.
The Kiswate Digital Academy is structured around 3 course components. Digital library. This will provide students and teachers with access to a vast array of digital textbooks and educational resources online, ensuring that learning materials are both accessible and affordable. 2. Learning management system LMS. This system will enable teachers to conduct remote lessons and allow school principals to recruit emergency or substitute teachers from a distance. It will also facilitate continuous learning for students regardless of physical location. 3. Scholarship system. This component will offer financial support to deserving students, ensuring that economic barriers do not hinder access to quality education. By leveraging these components, Kiswate Digital Academy aims to create a resilient and flexible educational environment. Students will have uninterrupted access to digital textbooks and teachers, while educators will be equipped with the tools needed for effective and remote teaching. This initiative not only addresses immediate educational challenges but also lays the foundation for a more robust and adaptable education system in Kenya, capable of withstanding future disruptions and fostering long-term academic success.